Ever where you want it, is it? Right, well, hopefully everybody can see that. Can we have some sort of thumbs up from somewhere? Bob or Brian probably might be better. Is that full screen now?
Yep, it's full screen as far as I can see. Yep.
Excellent stuff. Excellent stuff. Okay, we'll sort of ramble on a little bit to start with, as a number of people probably arrive. But thank you all for taking your lunch times to listen to part 2 of Masonry Arch Bridge Strengthening. I'm going to sort of continue on from where my colleague and co-director Bob Falconer gave you a very comprehensive insight into the theory of the Mars system, together with a number of case histories, some of which you will unfortunately see again today, because I'm pulling out certain aspects of them. Hopefully we will find interesting. I'm David Kitching. I'm Managing Director of Goldhawk and the Stress Group, and I've had the pleasure of working with Bob, our Design Director, and Brian Boughton, who is our Marketing Director, for that time, and it's been incredibly interesting and enjoyable. We've actually carried out too many projects in those 12 years to include in this short seminar, but I hope I'll bring you some of the interesting facts about the system and an insight into the installation of the reinforcement. For those of you who joined us for part 1, some of part 2 you'll find familiar, but hopefully not too boring. So to start with, I'm going to highlight just what we as a specialist company are trying to achieve. And I think you'll find that we've, between us all here, got many common goals. So we'll often run. So today we're going to talk about the Mars system. There is another part of what we do, which is the Mars system. We do a lot less of it because there's really no budget for strengthening parapets, but we have done them in the past, and it will be one of those things, I think, in the future that will get consideration for reduction of collateral damage from impact into parapet walls. And it's something that, again, we can talk about sometime in the future. And unless we have a lot of time and I rabbit my way through this rather quickly, or quicker than I mean to, there may be some time just to take a look at that. But in the meantime, we'll concentrate on the Mars system. So here's some photographs of some lovely old historic bridges that we've been involved with, just to give you that idea of what it is that we're trying to achieve. And that is to save our historic bridge stock. These are incredibly useful structures. To keep them is so sustainable. That it doesn't make any sense to knock them down and stick a concrete bridge in if you can maintain them and bring them up to standard and in essence future-proof them. So you're going to reduce the overall expenditure of on bridge maintenance, and if you can do that, you can obviously reduce the costly disruption to traffic during any strengthening or repair, and by doing it this way, you're going to minimize the carbon footprint of the process. We know that modern loadings are much higher than the bridges were ever designed for, and obviously to be able to strengthen up to take those loads is really important. And one of the things that's with climate change that's becoming ever more common is flooding, and we've seen bridges over the last few years. Certainly old bridges take the punishment of flood water. So again, if you can prevent or reduce the risk of that happening, that's got to be a good thing also. So we're obviously trying to prevent this happening. These are fairly well-known bridges that have suffered from quite often scour under the abutments, and this is something really that I don't know if there's anybody here from the EA, but it's very useful that we as engineers are able to have a look at the foundations of the piers and just check that scour isn't going to be a big issue. With the flooding that we're getting nowadays, the speed of water, quite often we're getting this sort of situation where in fact a bridge is knocked off its feet basically. And getting the access to the river for survey is very, very important. Here's some more examples. Well, they're pretty catastrophic. You certainly wouldn't want to be on any of those when they went. Top right hand corner, that's what you call collateral damage from it actually wasn't a parapet impact there, so you can see there's a machine on its side in the bottom left hand corner, which was for some reason working on the spandrel wall, and it went and it pulled a lot of the parapet with it straight onto the tracks. We imagine a high-speed train hitting that. Collateral damage would be atrocious. So again, this is somewhere into where making sure that bridges don't collapse is incredibly important. And probably one of the most uncomfortable things has been in the headlines recently is doing that. We really want to try and avoid that if we can, which is the infilling under bridges rather than strengthening them. And if we can reduce traffic issues, did you hear on the news this morning that in fact, well, London certainly is, I think it's top of all capitals in the world as the most congested. I can't believe that from Bangkok. I don't know if any of you have been to Bangkok. But anyway, it must be per mile or per distance per person or whatever, however they do it. But obviously, we all know how irritating it is to have to sit in queues of traffic. So if we can reduce that with our reduced bridge maintenance, then that's got to be a good thing. So let's look at some of the common faults you get with masonry arch bridges. I hope you can all see that. We'll start with the classic crack, which Bob mentioned last time, that you get between the flexible barrel and the stiff spandrel. And as he explained, you get that crack almost immediately you finish the bridge, because when you take the formwork out from under the arch, it having been built, that will compress, relax, and if the spandrels are already built, then you will already get some slight movement between the two. The bridges are perfectly happy like that. It's just that it is a problem, and it's a very common crack, and if it isn't dealt with and assisted, it will only ever just get worse. We've got ring separation, you can see there. This again is a measure of the flexural work that the arches have to do over time, and if the various layers of brickwork are sliding over each other, you have a general reduced capacity. So if you can bring and bond those rings together, you will obviously assist the bridge in distributing load. We've got spandrel bulging. That's a common thing that we come across, usually caused by the additional load that you're getting onto the bridge with heavier rail and freight, road, lorries, axle loads, depth of fill, because of course they increase the depth of fill quite often over a bridge, and that increases all sort of lateral load on the spandrels. So we look at how we can assist that, and it comes right down to, you can see there, sort of foundation issues, and we do come across those. The Mars system can't really assist with that, but we do highlight it as an issue and a problem, right into cracked wing walls through all sorts of movement that occurs. So the Mars system is really going to try and bring an arch up to a specified capacity. If you're the client, you want a specified load over the bridge, we will try and design it to, or we will design it to bring it up to that that load, or in fact, if you want it, maximum traffic loading. Once the mast system's installed, you've future-proofed the bridge. It will assist in reducing a lot of future maintenance. You've reduced deflection, therefore you're going to get less wear and tear. You've repaired the cracks that are in there at the same time as installing the masonry reinforcement, and you've rebonded the separated ring arches. So you've really rehabilitated that arch as well as strengthening it. And Bob has designed it so that in fact you can take some of the lateral load also at the voussoirs up into the spandrels. Can't go all the way into the spandrels, but certainly that area around the voussoir certainly will assist with any outward load. So this is a fairly old slide and it may have changed. My apologies if it has, but we believe that all bridges have now been assessed for condition and load capacity in the UK, and it's estimated that there are approximately 45,000 that are still under strength. Now that's all types of bridges, that's not just masonry arches, it's yeah, every type of bridge you can think of, composite bridges and pure steel. So what are the problems really with masonry arch bridges? Well, one of them is that really they were designed for much lighter loads, and you can see a horse and cart here, very typical of the 1800s and before that. Probably maximum speed 4 miles an hour and a maximum load of about a ton. And of course, what we're now asking our bridges to take is huge juggernauts and some extra sized lorries. So heavy axle loads, high speeds, a lot of impact onto the bridge. So we're now going to run through what are our tools, current tools for strengthening. I've used this photograph of bridges, which I believe, I haven't checked this, I should check it, are actually in a part of Edinburgh. But they're rather nice. They show exactly what we need to show. But interestingly here, there's a brick arch with masonry spandrels. So the strengthening methods I'm going to just quickly go through are obviously overslabbing, which is a relatively common method of doing things. You can, and we've worked on bridges that have been sprayed underneath to increase the thickness of the barrel. Stitching by mini piling. Now we've never come across this, although we know it is a technique. The infilling, which you saw a photograph of before, and soffit reinforcement. Overslabbing, very diagrammatic, but that's exactly what it does. You're putting in an RC slab over the top of the bridge from abutment to abutment. And I think one of the issues with that is that it will tend with time to probably rot. And then you're going to create issues at the crown. And obviously then you're going to get an uneven load as vehicles go across it. And of course, you're going to have to dig the carriageway up to put it in, which means you're going to have to close the road. And we looked at all the traffic issues that there are. If you do deload, take a lot of the fill off, it's possible you might actually have to prop the arch while you do that. It's pretty costly, and of course you need quite a long time to do it. And while you're digging the road up, you probably need to dig up all the services and divert them. And I think we all know just how difficult it is to get coordination between our services and timings, and obviously the fines that go with it if you interrupt them. So if you can avoid that, obviously that's a very good thing generally. Here is spraying on the underside of an arch to, in essence, thicken the barrel thickness and increase capacity. But of course, it adds unwanted weight to the structure. I mean, possessions. I mean, you know, if you were going over a road or a railway, then the possessions to do that would be relatively long. And if it was something like, well, I suppose it is even a canal or a road bridge or rail, you've got headroom issues. So if it was electrified, of course, there'd be all sorts of problems. But the big thing about reducing the cross-sectional area is the flood prevention, because you're going to get less volume of water through there in flood conditions. And one of the things that we look always to be able to reverse whatever goes into a bridge, but if you put one of these sprayed concrete liners in, as it were, you'll never get it out without destroying the barrel, because it will always be harder than the barrel itself. And you've created something which is impermeable relatively. So water will tend to then be stored in the arch itself and the fill above it. And as Bob has mentioned, certainly, I don't know if you mentioned in the last lecture, but certainly has mentioned to us that you get from traffic going across the bridge a huge increase in hydraulic pressure if you've got trapped water in the bridge, and that really doesn't do anything any good. Pin piling, something like that, or pin stitching. Never seen it, but I have heard it's been done, and you can see how close to the arch it has to go to do its job. And basically, it's taking load from near the center of the bridge, near the crown, and distributing it down into the abutments. But it only strengthens for that one particular critical load case. And because of its location within the arch, it alters the response, and you lose that natural flexibility of the arch, which is incredibly important. You're going to end up concentrating stresses right at the edge of the arch, roughly at those third points, and you can permanently damage the arch by doing that. And it, of course, then you get ring separation, etc. You've still got to close the road because you're going to have to drill these things in incredibly accurately. I don't know how they were ever done. You've probably then got to divert services as well. So you've got all the same problems you've got really with overslabbing. We understand it's expensive and technically complicated. And once it's in, you can never inspect it. These things are too deeply buried to know whether you've got corrosion, breakdown of the grout. So it, you know, there are a number of disadvantages for it. Well, what do we say about this? Yeah, it's not going down too well with people, is it? So we know it's costly. We've actually bid for that bridge, funnily enough, and we know our costs were significantly lower than in filling it with concrete. And now that they've lost the appeal for planning, they're having to break it all back out. But it's an environmental and visual disaster. Imagine, you know, the flora and fauna that used that area to run through safely. They certainly can't now. You've permanently damaged the barrel if you were ever to try and take it out. Massive carbon footprint with all that concrete in it. And yeah, you've got all the disposal costs of the arisings. So I think it's not going to get much more favour as we go forward in the future. So we'll come to our fifth one, which is masonry reinforcement, an elegant solution. Bob will have showed you our graphic of the Mars system. That shows the elements of it. There's basically three elements: the circumferential bars, the longitudinal bars or lateral bars, transverse, I think we should probably call them, and the dowel bars or radial ties. So if we think about the system now, you've seen what it looks like graphically. I'm going to show you in more detail what it looks like in situ. Let's have a look at some of the comparisons that we get. So we don't add weight to the structure because the bars and the grout combined are probably slightly less than the small amount of stonework or brickwork that we actually remove. We don't reduce the elevational area, so there's no issues when it comes down to the Environment Agency. You don't really significantly change the appearance of the structure, and you will see this, and you probably saw it from some of Bob's case histories. And usually we don't require a road closure, so we can install this whilst the traffic or rail traffic pass over the top of the bridge. It's durable. We've got stainless steel and a type of epoxy, a hybrid type of epoxy adhesive that surrounds the resin, bonds it into the bridge, and prevents weathering and rusting. It preserves the inherent flexibility of the arches. As Bob pointed out last time, the flexibility of the arch is incredibly important. That's how it works. So you need to maintain that. But it does improve its structural behavior and elastics response. And as we said before, with those radial ties, we then repair and prevent future ring separation. It's cheaper than other practical alternatives. We kind of know that because it's so popular, and you know we get a lot of jobs, so it must have cost benefits. And of course, if you don't have to dig up the road, you don't have to dig up the services either. So when it comes down to bridge inspections, you really want to know how things are faring. It's easily inspected. You can as long as you can get under the bridge with very small tools, battery electric tools, you can actually take out a little bit of the Marflex around the bar and have a look at the bar, check it's all right. You will also immediately get an idea of how well that Marflex is still bonding into the brickwork. We've looked at some that go back over 25 years, and they're as good as the day they were put in. So we realise that the system works and maintains its performance. Bob will have shown you this. It's just a little recap really to take us into the next sort of practical phase of looking at how we install it. And this is the mechanism for failure of an arch, which I think you'll probably all remember very well. But what you really, I think, is the crux of this particular slide is that at C there, we've got the load coming down. That is the main failure hinge. Imagine if you put some reinforcement across the arch underneath at C, you would immediately put back that development of the fracture, the hinge. So if you do that all the way around, then not only do you distribute load, but of course it doesn't matter where the hinge will try and form, you're going to prevent it doing so. So a little recap for those who didn't hear part one. And here's this in practical form. These were full-scale bridges, a series of them that were put to failure, taken to failure by TRL, and the behavior and estimated capacities gave the guys doing it at the time the ability to look at programs for assessment of existing arches. I think Bob will have probably showed you something similar to this, if not this particular slide, showing the helibar as we're using it in this particular case in both directions. This is something we do very rarely, which is 3 bars. It's very complicated. It's quite technically difficult to install, and normally not necessary. So we'll try not to. But this basically just shows you 3 circumferential bars, a single transverse bar, and the hooked radial tie. You'll see the size of the slot. Maximum size of slot we ever put in is about 50 millimeters. Generally, it's around 35. So let's look at some of the practical aspects of installation. So you can see there, I mean, access is critical. You've got to be able to get down under the bridge and access the arch itself. We'll show you how we cut the slots, drilling of the radial ties, preparation for inspection. Preparation inspection, I mean, this is incredibly important. This is quality control. And then we'll show you the fitting of the stainless steel and the bonding of that steel into the masonry. So here's a couple of the bridges that you saw earlier on. That's actually Thrapston. It's a listed bridge in Northampton, which shows you the use of a pontoon incredibly well. We work with the EA on this sort of issue. They need to have them removed within 1 hour of a flood warning. So we have to design it to be able to get under there. And in fact, when we did the navigable channel on this particular bridge, we used a motorized float scaffolding. Scafloat, they're incredibly good for this sort of thing. And then once we'd got off the navigable channel, then we could use the pontoon system. And as you can see, it gives you a fantastic working deck. It can float up and down, doesn't restrict water flow. And it's only really when you've got flood danger that you would need to remove it. Bottom right-hand side, you can see something a little simpler than that. We quite often do these on the smaller arches if the river level is quite low, and that is a trestle and board system, which again can be easily removed within that specified hour. For a job we did in the Midlands on a canal, this is at Broad Street, we actually used a fixed scaffolding. So this was ladder beams spanning the canal with a full deck on it for a period of 12 weeks, where we were allowed to shut the canal. And as you can see, it gives you fantastic access to the soffit. And you'll see photographs of that a little later on. This is less usual. This is for Network Rail, a case history that Bob will have shown you last week, or when we were part 1. And unusually, we are propping the arch. But as he explained, this was an incredibly flexible arch. It was bouncing something like 10 millimeters with a freight train going over it. And for technicians to work under there with rippling brickwork meant it just from a health and safety point of view, it couldn't be allowed. And so a soft propping system, which would take catastrophic load if it had to, but allowed the arch to flex, was installed. So Maybes did that for us. And there was a neoprene gasket on the top of the props that allowed the arch to flex. But mostly we don't prop arches. So here we are with the cutting. Now, this tool was, I think, invented by Hilti a long time ago, 25 years ago, I think. And mainly it was used for electricians and plumbers to be able to chase into blockwork and create channels so they could put in pipes, cables. But it's powerful. It's vacuum recovery, so we don't get dust flying everywhere. That picture on the left is actually in operation. It's not just somebody holding it there, and there's no dust flying about. I don't know how many of you have been to site. We've been even on network rail jobs, and there's a guy with an angle grinder and a mask and a pair of goggles in a cloud of dust, and he's trying to grind out bed joints with a mortar raking blade. Those days have gone. When we actually show them how fast they can remove mortar with this, they just pack in completely and buy one of these things. It cuts a very accurate slot, any width you want, any depth up to 45 millimeters, very accurate. Literally, you can adjust that within a millimeter. And as you can see, it makes a very, very clean cut. So the yellow marks is the setting out. And in fact, the guys prefer to use those at the center of a wheel line rather than guided on the blade line, which you get off a little gauge on the machine itself. But these are phenomenal. And you can see ideas, examples of us using it there. You can get into a very small space with it. Some people have said, "Oh, can't you mechanize this? Can't you get a saw that just works its way around and cuts it?" Well, we actually have tried that, and the only saws that are available come with a straight track. So on a very large arch, you can actually cut segments like that, but that doesn't give you the shape of cut that you actually need. You need consistency and to be able to follow the curve of the arch. And if we look back at that network rail arch, that actually had it was an elliptical arch. In fact, there were 3 ellipses in there. If Bob, you might correct me, so that you actually have a change in radius as you come around the arch. Well, if you had to buy tracks of a specific radius for your bridge, you couldn't then keep moving them around to take the track round. So in fact, it just becomes impractical to do it. And this is without doubt, the best way of doing it. So here we are. This is a bridge for Oxfordshire. And again, just cutting into stonework. This is the bridge in Birmingham at Broad Street, and you can see there that the blades are twin blades, and they leave what we call a little biscuit in between, which very easily snaps out, and then we check it for depth. So you get that very accurate cut. This was at Newcastle Station, beneath the old station, not used for rail tracks anymore, but with some rather strange movement in it. And Bob designed a system to reduce the risk of further damage. You can see where all the bricks have been replaced. Actually compressed into position with wedges while the grout went off to get compression back into the bottom ring. And we're just completing the cutting there. Radial tie drilling. Now, for those of you who've dealt with the Environment Agency, one of the restrictions that they impose is making sure you don't contaminate the waterway. So you can probably see you have to have a little bit of tolerance between the edge of the pontoon and the arch to allow for height movement. And, you know, pontoons don't come exactly the same size as any arch. So even though you make them up of modules, you will get to within a certain size. And you're normally within about 300 mil of the edge. So any dust that we create, if it drops into the river, we're contravening our permit. So we use vacuum recovery even on our drills. This was actually taken, I think Bob said last time, actually, during COVID. We were working on the bridge during COVID, and because we had those ventilated masks, we could work as a team. So in fact, we were back work within 6 weeks of the shutdown. Clean and tidy. Well, you've seen that we use vacuum recovery all the time, but it doesn't mean that there aren't bits and pieces that fall, bits of mortar drop out, bits of brick. And also, as you saw, that little biscuit can often be left between the 2 blades and has to be snapped out. So you put polythene down over the pontoon or your decking, and at the end of the day, you remove everything and you roll it up, you take it up to the skip and you shake it out, and then bring it back to site the following day. There's no need to use new polythene all the time, and it just prevents any particles getting into the waterways. So quality control, incredibly important. I mean, if you think about it, we are bonding reinforcement into masonry. It's got to stick, and the stresses from the masonry have to be distributed into the steelwork. So the cleanliness of those slots, the accuracy and cleanliness is paramount. So when they're cut, they're each checked for depth with a depth gauge for that particular design throughout. It goes right the way around, and we mark the soffit with any areas that don't meet specification, and they have to then be ground out. So that's depth. Cleanliness, absolutely paramount again, because it's a bit like trying to put a sticking plaster on a wet finger. It's going to come off. So we need to make sure that we get full bond between the Marflex and the substrate. So these are vacuum, jet washed, scrubbed, dried, and made sure they're clean. So the inspector will go along and he'll run his finger along, check it, and if there's any residue on that, it gets washed again. So that's all part of the inspection. We even do that. You can see there in that top line that there is a hole, or a couple of holes. In fact, you can see 4 holes. They are the positions of the radial ties at the node. So where the 2 bars cross, or 3 bars, or even 4, the radial tie will come through and hook over it and bind everything into substructure. We check those holes for depth, for cleanliness, so that you get a full bond. Here we see some brickwork. This is a project that we're working on currently down in Cardiff for Network Rail. And again, you will see that just incredible cleanliness of the cut, which is really, really important. What you also see there are the fixing mechanism that we've got at the moment, which is a series of cable ties, give you a very accurate fixing, and those are into plugs that sit at the right depth so that the bar is tight against the plug, but it gives a minimum 3mm gap at the back of the bar into which we need to get the Marflex, and holds the bar right in the center of the slot, which again you will see is one of the quality control issues that we have to overcome. More examples. We're actually not ready for fitting of bar. Well, we are on part of the structure at the moment, but we're waiting for clearance from Network Rail on something else, and so we're working on making sure that everything is super clean and tidy at the moment before we start fitting steel. But I will show you some steel on that. So when it comes down then to fitting the bar, it's relatively straightforward. It's the fixing of it which is more difficult. So the bars come round into the abutments and generally go at least 1/2 meter down into the abutments and are anchored there. We then run the first circumferential bar round before then fitting the transverse bars, and then the second, in this particular case, second circumferential bar is fitted into the slot. That's that rail bridge for Network Rail that you saw there with the bar being fitted. And here's some examples of bars in situ, ready for inspection. I think there's much more to say about that. This is actually Betinox bar, also made full Helifix. We get it through Helifix, and it's a stainless steel ribbed bar. It's got a higher tensile capacity, and we use up to 8 millimeters in diameter of this material. On bigger bridges, you have to have a fairly wide radius to make this fit properly. Then you can see the radial tie hooking around it. Here's some more. This is where we got a mixture of lateral or transverse Betinox bar and circumferential Helibar Super 6. Now the Super 6 is like 6 millimeter Helibar, except the core is a greater diameter, so they are stiffer with a higher capacity, but still in relative terms very flexible. So now we come on to the again the quality control. So when we get to a position where we're ready to look at the fitting of the reinforcement, we look at absolutely everything. Is the bar actually going to stick over the surface? Because if it is, it's not going to be protected. So we need to look at exactly where it is in the slot. I pulled up 3 slides here. Now, from what I've told you already, you guys are looking at that. Would you say any of those 3 examples there are ready for grouting, ready for popping of the Helibar, the Marflex into the slot and bonding it in? I know I'm not going to ask for, it's a rhetorical question really, but the answer is no, they're definitely not. I think you can see top left that the transverse bar is tight against one side of the slot. That's no good because you're not going to get a full coverage of Marflex. Bottom left, exactly the same thing. You've got that transverse bar is sitting tight against the side of it. So we'll check for depth, gaps, and tightness to the slot. Top right, that's something different. That is the Helibond grout that's been used to bond the radial tie into the arch, and it spilled out because there was too much put in it. So as you push the bar in, it pushed the grout out, it was left, and of course you're not going to be able to get Marflex grout over that and protect the bar. So that's got to be chopped out. So we look at all these aspects until we get something like this. So we want to see those bars with spaces around them, equally spaced between the slot, and not proud over the surface so that they can be protected. And that is ready for Marflexing. So when it comes down to bonding into the masonry, this is probably the trickiest part of the whole journey. Marflex is a product that's made for us specifically for this purpose. It's a high strength epoxy with flexibility, and it's moisture tolerant, which is probably one of the most important things, because I don't think we've ever worked on an arch that's absolutely dry. It's always got a dampness somewhere, because of course you've got precipitation onto the road or rails above. They're not designed to be waterproof, and so the masonry arch itself is always damp. So whatever we use has to be moisture tolerant and has to stick to a damp substrate. So it's probably one of the stickiest things on the planet. If you go to site, we'll give you a set of overalls to wear as you go on to the pontoon. You probably won't go within 6 feet of the adhesive, but I guarantee you'll take some back with you because it'll be on your boot, or somehow you've got it on your elbow or your collar or even in your hair. It's remarkable stuff, and its pot life is relatively short. So we knock it up in 10 kilo batches. It gets loaded into cartridges, and then, as you can see it there, it's actually gunned into position very much as you would have a skeleton gun. We use pneumatics to drive the guns, but in essence, that is the most effective way we have ever found of delivering it. It's controllable, and you don't throw expensive bits of equipment into the skip at the end of the day because you can't clean them properly. And we've tried them. We've tried everything. We've tried pressure pots. We've tried mechanical screw worm drive pumps. But literally you throw them in the skip at the end of the day because you can't take them apart, and they're just ruined and not reliable. So in fact, this works. We load the material into 75mm diameter black tubes, drain pipe basically, which is reusable. Actually, you can clean them relatively easily at the end of the day, and they can be reused. But in general, you've not got a lot of wastage if you need to throw out a cartridge that's damaged, and saw off another bit of 75mm pipe. Now we can see on the top right corner the finishing process. Now, to get this Marflex into the slot, it has to be done in two phases. You have a guy injecting into the back of the slot, and you'll put enough in to make sure it oozes round the bar at the back, down into the first, between the first and second bar, if there are two bars, circumferential bars, and a guy will go around with a finger trowel, which that top guy's using on the right, and he will push it right into the slot to make sure that you exclude the air and you push that Marflex right to the back of the slot. Then following that, wet on wet, is another guy, again with another gun, and he will then push Marflex into the slot to cover the second bar and any radial ties. And again, with a finger trowel, that's pushed into the slot and then finished off, funnily enough, with fairy liquid and water. That's what gives you a lovely finish because it doesn't drag. You don't need to use a solvent, and it dries perfectly well. So that's why you see that looking a little shiny. But there's a real art to that. And the pot life of the material at 20 degrees is probably no more than about 40 minutes. So we have to get that loaded into the guns and into the slots pretty quickly. What do finished arches look like? Well, there's a lot of hoo-ha about cutting into arches, and particularly historic ones, which this is. This is a listed, part of a listed viaduct in Northampton, Oundle North Viaduct. And you can see there that although we had to deal with the environmental officer, the heritage officer for Northampton, who didn't like the idea at all. We did trial panels for him. We showed him the colour. He agreed that would probably be all right, but came to site when we finished and was utterly delighted. You can see the history of the arch. Yes, it's been strengthened, but actually you can see where it's been strengthened. So if you go into a museum, for instance, and you'll see a repair to a statue, and the marble is sort of brownish, it will have a white arm on it. Well, that is all part of heritage repair. You show what's been done. You don't try and hide it. You don't try and make it too obvious. So here we've got the Marflex grout adhesive in grey, and it's not a bad match. But could anybody tell me what colour grey we should use? Bottom left, how many different shades of grey have we got there just in one panel of brickwork? So this is the problem. If you go under a bridge, you try and colour match things. There is no. You will have 21 different shades of stonework or brickwork within a square metre. So you can't necessarily hide it. You just make it look as appealing as possible. And I think you can see here that's not too bad. This is that arch you saw for Oxfordshire and Milestone, where we had just the trestles. You can put trestles down on that, and that's what that arch looks like. A fairly random size stone arch, but again, it's fairly neat. And of course, you can imagine floodwaters going through there. They've got no restriction, and no problem. I'll come to floods in a minute. And there's the main arch in that particular structure. All very neat and tidy. And although that was what we call buff, and you've got a general colour of sandstone, I guess, it's got lichen on it. Some's green, some's black, some's much paler. There's render repairs in there. There's all sorts of bits and pieces. So you can never be exactly colour matched. And that's the bridge finished. So again, it's repaired, but you don't really notice it unless you actually go under there, and most people would canoe through and not even notice that it's been strengthened. Here's a bridge we did in Calderdale over the Rochdale Canal. That was quite a funny story. We got the order to do the work, and we got a permit from, well, we applied for a permit from the Canal and Rivers Trust to put our pontoon in the water and shut the canal for, I think it was going to be about 6 weeks. And about a week before we were due to start, we were refused access to the canal, saying no, they didn't want their bridge strengthened. So it was at that point that we had to point out to them, in fact, it wasn't their bridge, it was belonging to Calderdale Council, and they did want it strengthened. But we'd missed that window, because you can shut a canal for a certain period over the winter when it's not being used, but it still has to remain open for maintenance. And in fact, we had to postpone the project for a year and come back the following year. But that bridge was taken from, I think it was about a 5-ton weight limit to a 40-ton capacity in 6 weeks. Again, unless you walk under it, and I have done a couple of times just to see how things are faring out. This is up at, where is it? Where it is, God, I can remember the name of the pub just down the road, but it's at, it'll come to me in a minute. Yeah, unless you walk under it, you wouldn't even really know that's been strengthened. This is one for Essex, just showing you really the red mortar, which we very rarely use, and you can see, yeah, what colour red are you going to pick? It's orange through to sort of, you know, a deep sort of rusty colour, through to a light, you know, light coloured, almost grey. You can never get it exactly right, but that's what it would look like if you went in the rain in red. Now here's an interesting one. That's the bridge before we repaired it. Bob showed this last time as a little case history. You may have remembered it, but I wanted to pick out the fact that due to wear and tear, probably loads it wasn't designed to take, farming machinery and that sort of thing, you can see the stones have been punched down through, and some of them were up to about 80 millimeters of punch straight through the arch. And they decided to strengthen part of it by bridging it with a couple of iron beams and then infilling with concrete to try and prevent further punching. And it just got worse, really. So in fact, we removed. We didn't actually shut the arch. We worked with the traffic. It was a fairly light used lane, but trouble is you don't realise just how many deliveries nowadays come to farms and that sort of thing. DHL and such like. So in fact, yes, we chopped all that concrete out. We jacked those stones back by digging away the surface of the road in the various spots and punching them actually back to level, pressure grouting them into position. So they acted then in full compression. And as you can see there, then we fitted the Mars system, which has taken it up to strength. As you can see, Bob has brought that down into the piers. And I can't remember exactly why that was, but it was due to, I think, the shallowness of the arch and the necessity to beef up the piers to take the additional load. We can even work in fairly small culverts, as you can see that one for Network Rail out at Little Bedwin. That had water coming through. It was a relief channel for the river, and probably the tightest one I think we've worked in, less than 1.5 meters across. But as long as you can actually get in there and either sit or even sometimes lie down, you can actually install the Mars system. That was one for Essex. But you saw that earlier with the, that was before we started work. But you can see here, again, interesting photograph of you can see that the roadway and the bridge width has actually been extended over time, and you have 3 different arches. And we quite often get this. We've repaired a number that are 2 different arches, and I'll show you another one in a minute, where you get a completely different radius and not possibly a different barrel thickness. So that all has to be investigated, and Bob will do an individual design for each one. And in fact, if we go back, I don't think I need to go back too far. Going the wrong way. There. Can you see that is that same arch? And just to the right there, you've got the next arch, the middle arch, which has got a different pattern of Mars strengthening. So I think the tightness of the circumferential bars here was I think about 130, which is probably one of the tightest we've done, whereas you're getting on for nearly 450 on the other arch. So you only put as much reinforcement in as is necessary to strengthen the arch. So culverts, tight little culverts. So as long as you can get in there and work safely, then it's doable. And that's it finished. So again, you see all very neat and tidy, and you're preventing, if there are any cracks that had been in that arch, and we come across quite a few cracks that run around the arches, you've got reinforcement now bridging those cracks and helping prevent future cracking. Another little one we did for Hampshire and Skanska. I think they're milestone as well now. This was a little bridge, twin arch bridge that had got scour damage as well as under capacity of the arch. As you can see, fairly shallow, very little fill over the top of the arch. That's a 2-ring arch, and they wanted that beefed up, I believe, to 40 tons again. So we set about it and then found that the central pier was not in a very good condition. There'd been a lot of repairs, poor repairs done in the past, and scour action had caused a lot of damage to the brickwork. So part of the job was to replace those bricks, semi-engineering bricks. And as you can see here again, Bob has designed the reinforcement to come down into the parapet and provide additional stiffness. It's a good example of the bottom left, actually, of the cutter with all the little brick slips that have come out. Again, nicely contained on polythene, which can then be just rolled up and taken off site. But we've never had the EA ever come down and criticise us for anything, which is lovely. Rail bridges. I don't need to take you through what we did here, but this was a combination of strengthening and stiffening. So to stiffen the arch, we used one of our group's techniques, which we invented. To stiffen the haunches, if you remember, we actually injected the fill behind the haunches to create additional lateral resistance, which stiffened the arch. You may remember that. So you've got that top trace, dynamic trace, showing the movement in the arch. Once we'd done the stiffening, it was less than half, and then the installation of the Mars system then reduced that to a point where Network Rail were perfectly happy, and it got its route availability 10 category. That was that one finished. So I'm just going to finish off by mentioning flood damage. This was a bridge we were asked to look at, again in Calderdale, and again this was the result of those terrible floods that they had in the Calderdale Valley some years ago. And what happens with washout, scour of abutments. Now, what I think is remarkable about that bridge is still standing, and yet 2/3 of the width of one of the abutments has actually collapsed. We couldn't, it wasn't a listed bridge, it wasn't of great importance, and we couldn't get any heavy equipment to this side of the bridge because the only access was from the far side, from the main road. To be able to do anything with that, we'd need piling rigs to put down some for decent footing. So repairing it with the Mars system really wasn't on, but it just shows you what can happen with scour. As you can see here, this is Tadcaster, and a bridge that collapsed during flooding. Again, scour that took that out. And we can see here another example of a bridge that has been widened. So we've got two ages of bridge there, although they followed the same pattern. And funnily enough, it was the old bridge that stood firm and the new part that collapsed. We were looking to use the same injection system that we used at Briscoe's bridge there for the Network Rail bridge. For stiffening the haunches, we were actually going to stiffen the alluvium beneath the new pier, but we looked at it and we didn't particularly like the constituency of that alluvium, and it was too much of a risk to take. So in fact, we didn't do it. That was a Balfour Beatty job at the end of the day. This was an interesting one. We were called in by Bam Nuttall, actually. Linton Bridge over the wharf, and they had water flowing through there during those floods nearly up to the crown of that bridge. And what happened overnight was that someone reported that they thought the pier in the center had dropped. And we were called up to have a look at it. Now, I didn't believe it had dropped. You can have a look at what it looks like. And so they shut the road. So when I got back after the survey, I went back and looked at Street View. There's a really good, you can go across the bridge on Street View, and there was one that happened to be about 6 months before that, a dated one, that was absolutely flat. So that had gone down 300 millimeters overnight. Nothing we could do, really much we needed to do. We did a little bit of temporary works there to stiffen it up. You can actually see, you know, that hinge. Can you see right through the middle of that from side to side of the picture? There is a dark streak in the brickwork. That actually is a crack that's 40 millimeters wide, which has been caused by one pier dropping and the arch opening, very much as you saw the mechanism for failure. So in fact, these were temporary works, no more than that. It wasn't permanent strengthening, so that they could actually get piling plant across the bridge onto the piers, and then they pile down through the piers. So I hope that's been instructive. I hope it backed up Bob's probably far more interesting seminar that he gave you a few weeks ago. But I'm really open for questions, and probably Bob, I hope you're open for answering some of the questions too, because we will probably get some more technical ones that will need your intervention. Have we got any questions, Matt?
There's nothing in the chat as of yet, so if anyone wants to take stage and fire away, or if your mic's not working, put it in the chat and I can read them out.
Whilst people are thinking whether there are any questions or not, I'll just take us on to the parapet thing. Obviously, if you need to go, please do. I hope that has been instructive and helpful. Come back to us anytime with queries and questions and projects if you've got anything that you think might be suitable. So parapet rehabilitation and strengthening, something we looked at, or we have looked at, for a number of local authorities, again, where collateral damage is a potential problem. So you're really looking to increase the containment capacity of the existing parapet to reduce the risk of injury and death, reduce debris spread, the collateral damage, be cost effective, because once you've damaged that, you've probably got to shut the bridge to be able to repair it. You may have all those sorts of things, and try and not alter the appearance of it. Here's some typical damage caused by vehicles hitting bridges. I mean, the most serious one there obviously being onto the rail line. A train had just gone through, apparently. You can see that the car that hit the parapet by the police car actually bounced back. So if you can increase the capacity of that parapet to take impact, the more chances that you've got retaining the vehicle on the road. But you want to try and prevent the spread of masonry onto whatever's below, and you can see that in that canal picture below. Had there been a fisherman down there sitting on the banks, or pedestrians walking along, or dog walkers or anything, there could have been significant risk of injury there. Here's Eddie Stobart again. Didn't quite make it across that bridge. This was one here in Surrey. You can see a cement mixer had made it down off the road onto the trackside. Quite a mess. I don't think anybody died. I think this was remarkable, but the lorry driver walked away from that. But you can see the parapet he took out, incredibly thin. So again, one of the problems is, had we repaired that, tied it all together, and he'd taken part of it out, will it have pulled the whole of the parapet down instead of part of it? So these are all things to consider when it comes down to it. I can't remember the code that this is from for parapet design, but it's all part of it. Obviously, these are the preferred safety barriers. Keep vehicles away from the parapet if you can, but quite often you haven't got the width in the road to do that. Anyway, by the by, we can talk about that another time. So, how are we doing on time? I think we're sort of around about on an hour and 5-10 minutes. Matt, is that?
Yeah, we are.
Everybody's happy with that.
We do have a few questions that have just come in just when you were speaking about that, though, Dave. So probably just fire the email quickly.
Yep.
So the first one from Ian: how do you determine the additional capacity and design life the system gives to a structure?
Ooh, that's one for Bob. He's gone to sleep.
I'm here. Camera's not working, I don't think.
Your microphone's working fine. So could you repeat the question? Could you repeat the question, Matt?
Yeah. So how do you determine the additional capacity and design life this system gives to a structure?
Yeah, it's just normal reinforced brickwork design, which is the same as reinforced concrete design, really. You have a lever arm. Reinforcement takes the tension, and the brickwork takes the compression. So we know the moment of resistance we want to achieve, and we design sufficient reinforcement to achieve that moment of resistance at the critical location. We can only strengthen the barrel up, there's a limit to how much we can put in, because there's no way we can over reinforce brickwork. So we have to make sure that it's under reinforced, and so it's a particularly thin barrel, and the local authority want a heavier load than that can take, then we can't strengthen up to that level. But I think we've only had one case in over 300 that we couldn't achieve the strength that the local authority was looking for. And that tends to be where you've got a new barrel next to an old barrel, then you don't get the load dispersion between the two, and that reduces the capacity of the bridge. But yeah, it's just normal reinforced concrete, reinforced brickwork design. Does that help?
And the length of time, we sort of say it's the design life of the remainder of the bridge, really, don't we, Bob?
Yeah, I mean, the Marflex is inert. We use stainless steel, which is protected against the salt water that you get percolating through masonry bridges. That protects the stainless steel. So the stainless steel is inert, the Marflex is inert, and as Dave has just said, we've looked at bridges that we strengthened over 25 years ago, and they're still as good today as they were 25 when we installed it 25 years ago. So I think it will last the lifetime of the bridge.
Any other questions, Matt?
Yeah, there's a few more. I'll probably go on to Ian's one just because he's asked that first initial question, and Ian's also said, how would you assess the structure in the future with this system in place?
Oh, that's one for you, Bob.
Well, you need to have records that how many bars were put in the slots, although you can easily dig out the Marflex and see for yourself. If you don't have the records, you can work out how many bars there are. You can measure the spacing between the bars, so you know how much reinforcement is in there, and then you can just calculate the strength of the barrel from that. So it's fairly simple.
And presumably all the design documents are part of the records for the bridge going forward. So the back analysis is there for those to see.
Although an awful lot of bridges we look at, the records have been lost, so I hope that doesn't happen in the future as local authorities change.
That's a good point. Right, question coming in there, Matt, I think.
Yep, just go through the other one. That's Ian. Another one from Peter was just, what's the expected design life for the system?
Yeah, we say basically the for the remainder of the life of the structure.
Yep, and then scroll down. Mike Wheeler, you've obviously asked for some examples of parapet reinforcing an expected load capacity. I know Dave, you were starting to kind of mention the parapets.
Yeah, if you'd like to contact us, as Bob knows, it's a very difficult one. And in essence, what we came up with was a system. And while we've got that photograph there, for those who can see it, and that brickwork really will over years, because as we know, mortar tends to weaken, and quite often you end up with what in essence is just a pile of bricks separated by a fairly dusty mortar. If you could increase the inherent density of that wall, you will increase its resistance, its lateral resistance, because the kinetic energy required to punch through it is got to be a lot higher. So in fact, we designed a series of compression ties that actually are drilled down through the parapet, and you squash the parapet. You actually put a load into it, and you do that every meter or so, and you increase the inherent mass of the parapet. And to reduce collateral damage, you then put reinforcement in it longitudinally, which with ties running through, so that if a vehicle hits it, the amount of brickwork that will then spray out onto the track is minimized, or road, or whatever. So those are that is the background behind it. But there's still a lot of work needs to be done on this, and a lot of research too. Anything to add, Bob, on that?
No, we've got a drone video of one of our parapet installations, have we not, somewhere?
We have. I'm not sure I've got it in this. Did you? I think you had
No,
it
no.
in yours.
No,
But,
no, I didn't cover parapets, but yeah.
I hope that helped, Ian.
Thanks, both. We did have two more questions, or people with hands up. So I had is it A up from Essex Highways. I saw you had your hand up twice. I don't know if you want to ask any further questions. If not to worry. I've got Dushi. Oh, sorry, go on.
Fine, it was accidental.
Not to worry. Move on to Dushi from
Yes.
Amy.
It seems to me that Goldhawk are involved for the whole process, right? And you offer a package. Would that include certification of the bridge on completion? Because you have all the information in front of you to design the solution. The obvious result of that would be for you to certify it.
Again, I hope Bob will correct me if I'm wrong here, but yes, that we do, Dushi. Yeah, we
produce all the certificates. Yeah. Mm-hmm.
Okay. Thanks.
So it is a package. Usually, we're asked to come along, provide a strengthening design for the bridge, and so there will be from AIP to design report, and then anything that goes with the installation. On the RAMS documentation, right the way through to then certification. Yeah, it's a full package.
Thanks.
Well, that sounds like it's. Is there any more?
I think that's it at
Sorry.
the moment.
I'll just quickly ask a final question. I didn't quite follow the solution when you tied the abutments. You installed ties into reinforcement into the abutment faces. Interesting to know what that was for.
The purpose, the purpose of that reinforcement is to stop them moving apart, because you get the lateral pressure from the traffic loading and the fill loading, trying to push the spandrel walls and the parapet walls apart. So we tie them together to stop them moving further. but the tie is, because there's relative movement between the barrel and the spandrel walls, the tie is flexible, because the Marflex is flexible.
Sorry,
I
I
mean-
mentioned the abutments. You had a slide there with the abutments, with reinforcement in the faces.
Oh, I see. Yeah, that's the one that Dave showed. They were false abutments, and they were actually acting as a pivot for the barrel. It's a bit difficult to explain, but they were false abutments, and we tied the abutments back into the bridge. If you see what I mean. There were it was a barrel that had been constructed wider than the waterway, and someone had come along in the past and narrowed the gap, if you like, and it would have been nice to take that part out and redo the whole barrel, but it just been too expensive and not worth doing. So
This was this little one,
yeah,
wasn't it?
yeah, that's
this,
it.
This
So,
was the one. It was quite unusual.
yeah, so they are false abutments. They were added later, and there's no point in taking them out, and because it had been strengthened by this by a
Well, it was an
steel,
infill, wasn't
steel
it?
bed, wasn't it? An infill steel bed.
Yeah.
Bridging, and that destroyed the barrel, and so we took that out. The barrel was in terrible condition above, and guys, it wasn't the easiest job in the world, was it?
Certainly wasn't.
Bring it all back, but they've made a fantastic job of that.
So,
But
the longitudinal bars in the soffit, on barrel soffit, where do they go? Do they get
you mean the
the longitudinal
bars?
bars? Where are they anchored actually?
The circumferential bars. Well,
Yes.
if you remember that diagram that Dave showed initially, the critical location for all sort of loads tends to occur in the middle third of the span. So we take the bars back to the springing, and that gives you sufficient anchorage for the bars.
So the springing there would be set back, wouldn't it, from the face? If that's a false abutment.
Yeah, I mean, we have we got a case at the moment where we are having to recase a number of parts of the bottom ring of brickwork, and when you recase, then there's no stress in those bars, so we have to take our anchorage further into the abutment than we normally do. But really, the bars are only required in the middle third, and the rest is anchorage. We only need about 600 mil for anchorage and get the full strength of the bar, but so we have adequate anchorage for the bars as it goes from the middle third to the springing.
Thanks.
No, thank you for the questions. Great question.
Did just have two more questions pop in,
Yeah,
guys.
great stuff.
So Waleed, for clarification, by reminder of life of structure, you mean that you will certify the system for the additional length of the structure requested by the bridge owner, so an additional 60 or 120 years, etc.
I always think this 120 years is a bit of a pie in the sky. How can you tell that something's going to last exactly 120 years, and does it fall down after 120 years? So I think we bring the bridge back to its original capacity, and that bridge has been sitting there for 100 years, 200 years, and I think it'll last another 200 years.
Yeah, I think it's exactly the point, Bob. The fact that big steel suspension bridges, I mean, they have to be designed for 120 years because it's a lot of money to spend if you're going to spend it do it for less. But in fact, as you quite rightly pointed out, a lot of the bridges that we work on have already been there for a couple of 100 years, and we're really putting them back or actually enhancing them in terms of strength and not just capacity, but operation as well. And so they should last without any doubt, at least as long as they've been there already.
Hmm.
Oh, your camera's working now.
I know, yes. I don't know if that's a good idea or not. Put people off. Mhm.
There's been some good questions today, actually,
Mhm.
and I hope, and it'd be lovely to get some feedback from our delegates on the usefulness of this this two-part lecture. It's the first time we've done it as a two-part thing, and any comments. You know, we don't mind criticism. You know, it's the constructive side of it. If we can improve on the delivery and give you more information, whatever it is, always useful to hear from people in any way, shape or form. So happy to get comments, and they can come through to Matt or myself or Bob. You should have our email addresses from your invites. And again, many thanks for listening. I literally hope that it wasn't a waste of your lunchtime. So I think we can probably, unless there's any more questions, Matt, I think we can probably wind up.
There was one more that's just coming from Eye Up Again. So it just asking if we get involved with spandrel walls as well as the parapet strengthening.
Well, we do, and it's quite often, as you know, as a result of being there, we find that spandrel walls have moved out over the barrel, and the stability. You know, you know, are they stable? Can they be maintained where they are? Bulging, huge amounts of bulging you get on spandrel walls. We're often asked, can we pull them back in? Well, no, not really. We do get involved in putting ties through, but that doesn't necessarily need our expertise for that. That can be done by almost any contractor. But in fact, we're about to start one for, is that for Leicestershire? I think we've picked up one through Milestone, which will have tie bars in it, into the spandrels to hold it in. What Bob designed was that the transverse bars come to the end, almost the end of the voussoirs. You see it there, and then are drilled up and into the spandrel brickwork, and then there's a diagonal bar that goes up from the transverse slot and also is anchored into the spandrel. So you do get a little bit of additional stiffening at that point in time, and lateral tying.
Stops the rotation of the spandrel wall and
yeah,
ties it back to the barrel.
Helpful or not?
Difficult. I think it was, yeah. I found it very helpful.
Yeah, I've got a thumbs up on that. So thank you.
Well, great. So, well, thanks everybody again. Please don't hesitate to call us anytime with any queries. And yeah, we love saving these old structures, and are happy to do that anywhere around the UK. Thanks a lot. Take care and speak soon.
Mm-hmm.